All right, class. Welcome back again. And apology for the software malfunction, but we get back right to our lecture today. Hope you're doing well, and more importantly, I hope your drawing sheets are doing well so far. Now, because engineering drawing is one of those subjects. If you don't practice, it will expose you immediately. Now, before we jump into today's session, let's take a moment and connect what we already covered. Because I don't want this to feel like isolated topics, okay? Great. Now, I want you to see the progression. And hence, let's go and do a recap of what we've been doing before. In our previous sessions, we introduced orthographic projection. In general, we said it's a method of representing a 3D object using multiple 2D views. Not just drawing for beauty, no, but drawing for clarity and accuracy. Yes, we also discussed something very important, the concept of reference planes. In this case, I want to jog your mind. One, horizontal plane. Think of it as just the ground or the floor where you are right now. The vertical plane. Think of it as a wall, like the one you're seeing behind here. Okay? And everything we draw must be related to these two planes. The horizontal plane, HP, the vertical plane, VP. I'll be using those terminologies. So we also introduced the idea of the observer. And today you're observing, hypothetically. And I told you, in orthographic projection, the observer must always look perpendicular to the plane. No shortcuts, please. Look at me perpendicularly, okay? No side glances, okay? Because the moment you tilt your view, okay, you introduce distortion. Then we moved on into the X and Y reference line. On paper, we must show both views together. So what do? We rotate HP at 90 degrees so that we do so what we do is just we rotate the HP downwards by 90 degrees, and suddenly both top view and the front view becomes visible on one sheet, one plane. Okay. So the key idea from the previous class is, if you remember nothing else from the last class, remember this. Orthographic projection is about representing reality without distortion. It is not artistic, remember? It's engineering, communication. Okay, let me ask you something. If you design a mechanical part here in Kenya now and send a drawing to someone in Japan, will they understand it exactly the same way? They have never seen your part physically. They only see your drawing. So the question is, can you draw can your drawing speak clearly without you explaining it? This is the whole purpose of orthographic projection. Now, up to this point, we have been discussing orthographic projection in general sense. We talked about planes, observers, principles, but today we go deeper. We move from theory to application. Because now we begin to answer, how do we actually construct the projections? And we start from the most fundamental elements. So today's focus, we are going to talk about orthographic projection of points and lines. Now, I know some of you might be thinking, points, lines, that sounds too basic. Let me stop you right there, okay? This is where most students either become very strong or very confused later. Because a point defines position, a line defines direction and inclination, and everything else, plane, solid, machines, etc., are built from these two, points and lines. So today I want you to change how you approach this. Don't just copy what is on this screen. Instead, imagine the object in space. Ask yourself, where is it? How is it positioned? How would it look from different directions? I said, focus on me perpendicularly. But now I'm talking about different directions. Your imagination, you can visualize it. And you'll never struggle with this projection ever again. If you don't visualize, every simple problem will look difficult. Visualization. And don't worry, if at some point you feel like, sir, my brain is rotating more than the plane itself, that's very normal. It means you are learning. Okay? All right. Now that we have connected everything from the previous session, we understand where we are heading. Let's now move into today's lesson step by step. So I'll switch to the slides and we'll begin with the orthographic projection of the points. Okay. All right, class again. I hope you're doing well. And more importantly, I hope you're doing sheets. As I said again, I always do what? Enjoying being beautiful. Now, I have projected here a screen for you to see as we get to start. And therefore, I will start on this orthographic projection of lines and planes. All right. Now that we have connected everything from the previous session, and we understand where we're heading, let's now move into today's lesson step by step. So I'll switch to this slide so that we can continue from where we left. If you've been following from our previous sessions, we've been building up the foundation of engineering drawing step by step. And today we move into one of the most important topics, orthographic projection of points and lines. Now, this is where things start becoming very practical because everything in engineering design, whether mechanical, civil, biomedical, electrical, just name all those professions, must be presented clearly in views. Today, I want you to focus one key thing, how a 3D reality is translated into a 2D view or 2D views. So don't just copy, understand the logic, and let's get started. Now, in this slide, we're just passing our main topic. We are going to discuss about the points, lines, planes, etc. But today's focus will be mainly on the points and lines because they are the building blocks. If you must understand this well, planes and solids become very easier later as we get to come to projection of solids. Okay? So today, think this as a foundation. And as I lay this foundation, I want you to pay very key attention. Before drawing end projection, there are three things you must define. First, the object. Okay. Ah, what exactly are you projecting? You're talking about an object. The second thing is the observer. And very important, the observer always looks perpendicular to the reference plane. The third is the location of the object. Where is it positioned relative to the HP, horizontal plane, and VP, vertical plane? If you miss any of this, your drawing becomes ambiguous. So always think, what is it? Two, where is it? Three, who is observing it? That brings us to what we call notations. This is where many students make mistakes. Notations. I repeat again. We use a standard system in most of the time when we're doing letters and numbers. I told you sometimes when we are labeling, we label using what we call alphabets in uppercase as well as lowercase. Now, small letters in this case, in this example, we'll be using like a top letters. The top view will be using like AB. Small letters with dash, okay, is the front view, and those are what we call A prime, B prime. The double dash is just what we call a double prime, is what we will be using them as a side view. Pay attention. In our lecture, moving forward, we'll be using what you call the small letters alphabets, for example, A, to represent what you call the top view, for example, A and B. But when we move to A prime, B prime, we are moving to what you call, they will be representing the front view. And we move further to A double prime, B double prime, will be moving to what you call the side views. Now, very important. Above and below refer to HP. Above and below. HP, horizontal plane. In front of you and behind you are the vertical plane. This language must become natural to you because all problems will use it. Beautiful. Now, let me transit to this one so that you can understand the logic in my explanation. Quadrants. Before you is just a slide having different quadrants. Now we divide space into 4 quadrants using HP and vertical plane, HP and VP. Imagine the 4 regions. But here's the key. We always convert everything into a 2D drawing using XY plane or XY line. So that this diagram is not just a theory, as you can see. It explains why we rotate views later. Okay. Now, let me move to that one so at least it's very clear for your understanding. We are talking about points. At this point, I like in quadrants. This slide is very important conceptually. A single point is placed in a different quadrant, but we must still want to see both of its views clearly. Okay? So, what do? We rotate, repeat again, we rotate the horizontal plane HP downwards by 90 degrees. That's why the front view stays where it is. Pay attention to the front view in the slide. Okay? And the top view moves below the XY line. This is the reason behind the standard layout, not just a rule to memorize. Now, the quadrant cases. The quadrant cases. Now, we focus on the first quadrant. Then, the most commonly used, observers see these 3 cases. 1, the point above. I would want to take you back again, but just pay attention to this. The point above the HP in the front view, or in the front of the vertical plane, sorry. So the front view above the XY and also the top view above the XY plane. I repeat again. The point above the HP, which is the horizontal plane, and is in front of the VP. So we say that is the front view, which is above the XY, and the top view below the XY. Okay. The second point is in the HP. The front view on the XY. And that point here is what we learned, that the vertical plane. So the top view is on the XY plane. So here's the rule, remember. Rule to remember, pay attention. Position relative to plane determines position relative to the plane determines position relative to XY line. Don't memorize, just visualize this. Now, when we move from points to lines, when we move from point to lines, a line is more complex because it has the length, it has the position, and it has inclination. You've done mathematics and you can define a point, okay, even in form of coordinates. We classify lines into 5 types. Pay attention. 1, perpendicular, parallel, okay, inclined at an angle, or inclined, let me be very specific, inclined to the HP, horizontal plane, inclined to the vertical plane, and inclined to both the vertical plane and the HP. Pay attention, I'll repeat this one. A line which is perpendicular, parallel, inclined to HP, inclined to VP, and inclined to both the HP and VP. And our goal is always to draw the front view and the top view. So let's start with the simple cases. A line that is perpendicular to the HP. A line that is perpendicular to the HP. Such a line which is perpendicular to the HP, its front view shows true length. Perpendicular to the HP, horizontal plane. Its front view shows the true length. The true length is just a point. Here, the first case scenario. The second case scenario, okay, a line parallel to both planes. A line parallel to both planes. So here we have the front view, and the top view will show the true length. The true length will be shown on the top view and the front view. So always ask, which plane is the in the line parallel or perpendicular to? Which plane is the line parallel or perpendicular to? That tells you everything that you need. Now it gets interesting. The third case. Incline to the HP parallel to the VP. Incline to the HP parallel to the VP. Let me project that slide. Now, if it's inclined to the HP line, but it's parallel to the VP, its front view shows the true length, but the top view is inclined. And that brings us to the fourth case scenario, when inclined to the VP but parallel to the HP. So in this case, the top view will only show the true length, because it's from the top view you'll be able to see the exact length, which is now perpendicular to your eyes. Now, but the front view is inclined, therefore it will never give you the true length. So the rule is the plane to which the line is parallel shows the true length. I repeat again. The plane to which the line is parallel shows the true length. Okay. Now, let's solve a problem. Okay? Let's do what? Let's solve a problem. We have point A, and this point A is 20 millimeters above the HP. Start to visualize now and see things perpendicularly. And it's not only 20 millimeters above the HP, but millimeters in front of the VP, above 20 millimeters, the HP, in front of the VP, 30 millimeters. So, if you want to solve such a case, how do we go about it? The steps are very easy. First of all, you've got to draw the XY plane or the XY line. Let me say use a line. And then you mark the front view above XY. When you're marking the front view above the XY, what does that tell you? You want to mark it at 20 millimeters above that one. Now project down to get the top view below the XY. Project it. Okay? So always the height is in the front view, the distance from the vertical plane to the top view. Now observe the difference. Point is below HP. So what do we get here? The front view goes below the XY as illustrated here. And the top view comes above the XY. Same process. Only direction changes. That is the pattern. What if we have multi-points? What if we have multiple points? Okay. If we have multiple points, then this changes. But it's all about handling multiple points on one reference line. Very important. Pay attention. Now the key idea is maintaining equal space between projectors and treat each point independently. So don't mix them. Precision matters. Okay. So if the line is inclined to the HP, now we solve a line problem. First, a moment. First, the line is parallel to the VP. It's inclined to the HP. The key idea, we start with one end. You draw the plan. Upon drawing the plan, you project the elevation. And remember, inclination appears in views where it's not parallel. I repeat again, inclination appears in the view where it's not parallel. So that one gives us two options, which we'll see in the next slides. Okay, this slide shows that the same line is line in different quadrants, but what changes here is the position of the front view and the top view relative to the XY. The method remains the same. So the method is constant, position changes. Method is constant, and what changes? The position changes. But what if the line is inclined to both? What if the line is inclined to both? This is very important. This is the most important case. The line inclined to both the HP and VP